Alright, today we are going to look at cardinality of sets. This is section 2.5 in your book. Now, some of this material, so let me just write that down, section 2.5 from your book. Yes, so some of this material is something we've already covered when we were doing functions, but it's always helpful to kind of go over them once again. Now, recall the definition of what cardinality is. Recall that for a set S, the cardinality of S is the number of elements that it has. It's the number of elements in X. Right? It's simple. So if, for example, S is A, B, C, then the cardinality of S, and you use these two bars to kind of denote the cardinality of S is 3. Now, your task is to look at some important cardinalities, right? So, or some important rules about cardinalities, and the first one is something that you must be familiar with. This is the first sort of this is the first rule or definition that you should know, and this is something we covered when we were doing functions. What does it say? It says that if you have two sets A and B, they have the same cardinality if and only if. So it's a two-way implication. Remember, if and only if means it's a two-way implication. Both of them imply the other, each of them, right? So you can go from one to another and then back. If and only if there is a one-to-one correspondence from A to B, right? So one-to-one correspondence is a bijection if you have a bijective function between them. Right? So again, what does it say? If the cardinality of A is equal to B, then that implies that there exists a bijection between them, a bijection or a bijective function. It means the same thing. Between A and B. And we also have the other implication that if you can find a bijection between A and B, then you know that this must be true. They must have the same number of elements. The elements themselves can be different, of course, but the number of elements has to be same. Right? This is the first rule. And now the second one this is also something that we already know. What does this say? It says that if there is a one-to-one function, and remember one-to-one means injective. If there is an injective function from A to B, then the cardinality of A is less than or the same as the cardinality of B. What does it mean? That A has at least as many elements as B. Right? Moreover, when A is less than or equal to B and A and B have different cardinalities, we say that the cardinality of A is less than the cardinality of B, and we write A less than or equal to B. The second part here, let me just highlight that in yellow. The second part here is just a sort of a technical detail that you should always be aware of. If you're writing something in the form of an inequality, right? And you know that B has more elements, then you can kind of get rid of this other line and just say that A is less than B. Right? So just that. The important thing to remember is this, that if A and B, or if there's an injection, if there exists an injective function between A and B, then you know that the cardinality of A is less than or equal to B. Right? It could also be equal, but it's definitely not greater. So, in other words, this can never hold true. A can never have more elements than B. And you can convince yourself of this fact. Try to draw a set A and then a set B where A has more elements than B. Right? So maybe let's just stick to 3 elements here. So B has 3 elements. And if we try to find an injective function between them, which means that each output has a unique input, then you know that these two elements kind of get left out. Ideally, you could do this. This is still a valid function if these two are kind of mapped to the same elements, but then this is no longer injective, right? So in order to keep it injective, you just need one unique input for each output. But if A has more elements than B, then that is never possible. So in other words, if A is greater than B, then you know that there can never be an injection between them. Right. Alright, that was the second thing you needed to know about cardinalities. Now let's go to the third one. So the third has to do with now infinities. What does it say? Let's read it out. It says a set is either finite or has the same cardinality as the set of positive integers is called countable, right? So a set that is either finite or has the same cardinality is called countable. Now this word countable has a very special place in discrete mathematics and in mathematics in general. Now, the intuitive definition or the English language definition of the word countable is something that we all understand, right? Intuitively, it means something that can be counted, right? So, countable means can be counted, right? And this would mean if you have a finite number of elements, no matter how strange your elements look like, right? This is a set of very strange elements, but it's finite, right? No, even if it goes until 1 million, right? You have like a million more entries here, but eventually it ends somewhere. right? If it's finite, then you can count them, right? You can enumerate them, you can tell how many are there. But there's a twist to it that even if you have infinite number, even if you have an infinite number of elements, an infinite number of elements, they can still be countable. If, now here's the big condition, if there is a bijection between that set, so if there is a bijection between that set and the set of natural numbers, right? So this first intuitive definition, this is something that checks out. The second part, this is something that kind of needs you to look at it, give it some time, and look at some examples, and only then you can convince yourself of it, right? So let's read this sentence again. A set that is either finite, so this was the first condition, right? That checks out. A set that is either finite or has the same cardinality as the set of positive integers is called countable, right? Natural numbers, sometimes people include the number 0 in it, so it's easier to just say or z plus, right? Some authors include the number 0 in this set, some authors don't. So just to be safe, you could skip n and just say z plus, right? Let's just say z plus here, right? And this kind of cardinality has a special name, and let's see what that is. A set that is not countable is uncountable, of course. So anything that neither satisfies the first condition nor the second condition, right? If neither of this condition is satisfied, then the set is called uncountable. When an infinite set S is countable, we denote the cardinality of S by LF null. So this letter, this weird looking character, is actually from the Hebrew alphabet. Okay, they already have it in here. So it's from the Hebrew alphabet, and then we say null because of this subscript, this small 0 here, right? So it's called Aleph null, where this strange letter is Aleph. It's very similar to the letter Aleph from Arabic, right? Where this is Aleph, the first letter of the Hebrew alphabet. We write S equals to, the cardinality of S equals to Aleph null, and say that S has cardinality Aleph null, right? So anything that has cardinality Aleph null is a set that is countable, which means that it either is a finite set, or so it's either a finite set or has a bijection, has the same cardinality as the set of positive integers, which means that there's a bijection between that set and the set of positive integers, right? Good.